So we're going to look at causal LTI systems that are described by difference and differential equations. So in discrete time, the general form of a difference equation, something that you've seen in your lab, is something like this. So it describes a linear combination of time-shifted versions of the output in terms of a linear combination of time-shifted versions of the input. Okay, so here, x of n is the input, y of n is the output. In continuous time, it's the same thing, except it's a sum not of time shifts, but of derivatives. So we have a linear combination of derivatives, higher order derivatives of y of t, set equal to a linear combination of the higher order derivatives of the input. So here x of t is the input and y of t is the output. So when this thing on the left-hand side only involves the k equals 0 term, well, there may be a constant in front, but we can always divide by it. Basically, that's the kind of a system that describes y of n as a linear combination of time shifts of the input directly. When k includes terms, so when k includes values in this range that go beyond 0, then you're starting to get what amounts to feedback, because you're saying something about how the output at time n and some terms that correspond to the output at previous times relate to a linear combination of time shifts of the input. Okay? So that's kind of like the accumulator. Remember that example we had, that y of n minus y of n minus 1 equals x of n. So that was an example of that more complex situation. Same thing over here. If k equals 0 is the only term here, well, basically you're saying dy dt equals some linear combination of derivatives of the input signal. But if you have something where k is bigger than 0, then you're starting to involve derivatives of the output in the equation as well. So how do you solve these things? We're not going to go into details here. In section 2.4 of the chapter, which you should read, so look in Oppenheim and Wilsky, second edition, section 2.4, they talk about, at least with some simple examples of first order systems, they talk about how, if you're given an input, x of n or x of t, how you can find the output. So basically what they say is, that's what we mean by the solution to that difference equation. You're given an input x, and you want to know what y is. So basically what they show is that you can represent the output as a sum of two signals. One is called the particular solution, one is called the homogeneous solution. So this is particular plus homogeneous. So particular just happens to be a solution that maybe you can find by some mechanism. So they give you some suggestions about how to find a solution to that. But here we want to find sort of the general form of the solution. And the homogeneous solution is simply the solution in the case of discrete time. It's a solution that satisfies the sum of a sub k y of n minus k equals 0. Yeah. Y sub h, the homogeneous solution. And then in the discrete continuous time, it's going to be the sum of that linear combination of the derivatives being set equal to 0. So if you get a solution, yeah. What's the problem? So this is the equation that these homogeneous solutions satisfy. And then you can usually have, for the particular solution, there's usually some form that you guess for it, a general form, and then depending on what the actual particular input is, there may be some constant coefficients that you have to nail down. But the key thing to observe, which they discuss, is that actually isn't quite enough. There are usually going to be some constants that are, when you go through this procedure, that you need to sort of resolve. And in fact, you need to say something more about the system that's described by this differential equation to get sort of a unique solution when you say, I put this input x in and I want to get y out. So what you need, in addition to all of this, is you need to specify some auxiliary conditions to sort of further characterize the system that this equation represents. And in particular, if it's, in some sense, I've already indicated something further about the system. I could have just given you the differential equation or the difference equation and said, this describes my system. Now, when I put x of t in or x of n in, I want to know what the corresponding y is. That won't be quite enough. You need to say something more about the system. So here I've said something about the system that I'm interested in. I'm interested in the causal LTI system that's described by that differential equation. So when the system is causal and LTI, the auxiliary condition that we use is what's called the condition of initial rest. Which kind of captures causality and the specifically time invariance as well as linearity, but you can kind of see it specifically for those things. And the condition of initial rest simply says that if x of n, the input, is 0 for all times up to some time n0, then the output is going to also be 0 for times less than n0. So in some sense, until something happens in the input signal, nothing's going to happen in the output signal. Zeros input up to a certain point is going to be zeros in the output up to that point. And likewise for continuous time, the same kind of condition.